Hi, this is Dr. Goldstein, and I am going to discuss implicit differentiation. I am going to do this primarily by means of this example, which I have written here. So we start with an equation, 2y cubed plus y squared minus y to the fifth equals x to the fourth minus 2x cubed plus x squared. And we can talk about the solutions of this equation, meaning pairs of points x comma y that we can plug in. And these solutions form a curve, and that's the curve that you see at the right here. So the solutions of this equation form a curve. So for example, if I take the point x comma y equals 0 comma 0, and I plug that in, so I get 2 times 0 cubed plus 0 squared minus 0 to the fifth equals 0 to the fourth minus 2 times 0 cubed minus 0 squared. We get 0 equals 0. So this point x comma y equals 0 comma 0 is a solution. And here we see it over here, right there on the graph. So one of the things that you probably notice looking at this graph is that it doesn't pass the vertical line test. So this does not pass the vertical line test, which means that it's not defined by a function. It is not a function. So over here in our equation, we look at this, and there's absolutely no way that we can solve for y in terms of x. We cannot solve for y in terms of x. And so y is not a function of x. Okay, but if I look at this picture, I still have tangent lines. If I have this point, I still have tangent lines. And so we still want to be able to take derivatives. And in order to do that, so in order to take derivatives, e.g. to find tangent lines, we treat y as a function of x. So it's not a function of x. We say that y is, quote, defined implicitly by x. And this is why this method that I'm about to show you is what's called implicit differentiation. So the idea is if we're going to treat y as a function of x, if we're going to take its derivative, we need to use the chain rule. So you need to use the chain rule to compute derivatives. So for example, if I'm going to take the derivative d dx of y cubed, this isn't just a variable cubed, it's a function cubed. So I have to take down the exponent, subtract 1 from that exponent, and then I have to take the derivative of my function. This is my chain rule. So a typical way that you see this written is 3y squared dy dx. That's my preferred way of writing it. You may also see 3y squared y prime. So this is y prime But I actually prefer not to use that notation. I prefer to use the dy dx because to me this prime gets confused with a 1. Is that a prime? Is that a number 1? So I actually prefer using this notation because I just think that it's a little bit clearer. Okay, so let's see an example of this in action. So again, here is this equation that we're starting with, 2y cubed plus y squared minus y to the 5th equals x to the 4th minus 2x cubed plus x squared. And I am going to take the derivative of both sides of this equation. And on the right-hand side, it's very easy. On the right-hand side, I'm just taking a normal derivative d dx of x's. And so I end up with 4x cubed minus 6x squared plus 2x. Now, on the left-hand side, I have to use the chain rule whenever I'm taking the derivative of y, because y is a function of x. So on the left-hand side, I have this 3y squared times the derivative of y cubed. So again, this is because I have to use the chain rule. And then I have 2y, that's the derivative of y squared, times the derivative of y. Ooh, there is a typo here. Oops, that should just be d dx of y, and this should also just be d dx of y. This inside function is just y, and that is what I am taking the derivative of. In the third term, we take the derivative of y to the 5th, and we get 5y to the 4th times this derivative of this function y, which is our inside function. So again, in all three of these terms here, we're using the chain rule with this inside function that is y. Again, y is a variable, but we are treating y as a function of x. So when I simplify all of this, we get 6y squared dy dx. Again, you'll see that written as y prime sometimes, plus 2y dy dx minus 5y to the 4th dy dx. And then don't forget about the right-hand side. It was so easy. We did it so long ago. This is equal to 4x cubed minus 6x squared plus 2x. So now that we have taken the derivative, so this entire thing here, this is all taking the derivative. And I have this term dy dx that appears in all three of these terms. I want to solve for that, and that is my derivative of y with respect to x. So we want to solve for dy dx, because this is the derivative of y with respect to x. And that's what we're looking for. We're looking for this derivative. So first I'm going to factor it out. I take dy dx out of all three of these terms, and I have 6y squared plus 2y minus 5y to the 4th. I still have this right-hand side over here, 4x cubed minus 6x squared plus 2x. And I divide both sides by the 6y squared plus 2y minus 5y to the 4th. And I get dy dx is equal to 4x cubed minus 6x squared plus 2x divided by 6y squared plus 2y minus 5y to the 4th. So this is our derivative. And it represents how much y changes as x changes. That's what that dy and the dx means. It's the change in y over the change in x. One thing that you will note is that it depends on both x and y. If I want to get a number out of this, I have to plug in an x and a y coordinate. And this is because in order to get a tangent line to my implicit curve, I need to specify both coordinates. So I need to specify both coordinates. To get a slope. And I am going to show you an example of that in a little bit. But first, let's look at a slightly more basic example. So let's look at this curve again. Again, the picture is in the lower right-hand corner. And let's look at the point 0, 1 plus root 2. So that's about right here. And we're going to look at the tangent line at that point. So remember the derivative, which is dy dx, which is this equation. When we plug in a solution, x comma y equals ab, we get the slope of the tangent line. At that point. The same as we did before with derivatives, except now we don't just have one coordinate, we have two coordinates. So using this point, when we take our derivative dy dx and we evaluate it at this point, 0, 1 plus root 2. So again, this vertical bar is how we denote evaluation in Leibniz notation. We have 4 times our x-coordinate 0 cubed minus 6 times 0 squared plus 2 times 0 divided by 6 times our y-coordinate squared plus 2 times the y-coordinate minus 5 times the y-coordinate to the 4th. When we evaluate this, we get 0 in the numerator and negative 130.05 approximately in the denominator. This is an approximate. But what we know is that our derivative is 0. And if we remember, what does a derivative of 0 mean? Well, it means that we have a horizontal tangent line. So we have a horizontal tangent line at this point, 0, 1 plus root 2. And we can see that in this picture. We can believe that at this specific point we have a horizontal tangent line. So let's look at another example. If we look at the point 0, 0, which is the solution that we looked at before, this is this point right here. And you might notice that on the graph that looks like a slightly strange point because the curve goes around and through that same point again. Well, let's look at the derivative. So if we take the derivative, if we take dy dx and we plug in this point 0, 0, so we plug in x equals 0 and y equals 0, we are going to get, okay, so 4 times 0 cubed minus 6 times 0 squared plus 2 times 0 divided by 6 times 0 squared plus 2 times 0 minus 5 times 0 to the fourth. This is 0 over 0. This is undefined. Remember, this is a function that we are plugging into. This is not a limit or anything. So this is just undefined. So what the derivative tells us is that there is no tangent line at this point 0, 0. In fact, there isn't going to be a tangent line anywhere where the denominator of that thing is equal to 0. And when we look at the picture here too, we can see that, yeah, we might have trouble defining a tangent line at this point because we don't know whether we want to use this as our tangent line or whether we want to use this as our tangent line. There's two different curves that cross through there. I mean, it's all the same one curve, but we don't know which part of it to use. So what we see reflected in this derivative that we found implicitly is that, yeah, sometimes we do not have a tangent line because this formula that we found is undefined, and that is reflected geometrically in our picture. I want to show you one more kind of fun thing that happens when we are looking at curves with implicitly defined derivatives. So we can talk about the tangent line when x is equal to 1/4. So I'm only specifying an x-coordinate here. I'm not specifying a y-coordinate. And if you look at the graph of this curve and you think, okay, where is x equals 1/4? There's a lot of different y values that we could potentially have. So these are all along this line. X is equal to 1/4. It looks like there are 5 different y values that we could have. So we ask ourselves, sort of as an aside, well, what is y? We have to have a y-coordinate to plug into this formula. Well, we know that we have this equation 2y cubed plus y squared minus y to the 5th is equal to x to the 4th minus 2x cubed plus x squared. And so if we plug in x equals 1/4 over here, what we end up getting when you plug that in and you simplify is you get 2y cubed plus y squared minus y to the 5th is equal to 0.0351563. Gross. And this is a degree 5 equation. You don't want to solve this by hand. What we find via a computer, so this is just an equation that we solve for y, and again, it's just too hard to do by hand. From a computer, we find that y is approximately, so I don't get exact answers from a computer, I just get approximate answers. Y is approximately 1.61573. That is that top point right up there. The second value that I get for y is 0.163085. So this is this point right here. I'm going to color code a little bit. I also get that y is approximately negative 0.271457. And so if I wanted to color code that point, this one is this point right here. And I do indeed get 2 other points, 2 other y coordinates. I get negative 0.477027 and also negative 1.03033. So those are those other 2 points down there. Now, looking at this curve, what we notice about these points is that the tangent lines that go through them are all different tangent lines. This one looks like maybe it's about there. This one looks like it's maybe about here. So not only do we have totally different tangent lines at these different y values, It's all the same x value. It's all x equals 1/4. But we should get totally different tangent lines with totally different slopes at these values. And again, so we can see that reflected in our computation. So if we actually calculate dy dx at the point 1/4, 0.163085, what we end up getting, and again, you plug the x-coordinate in for x, you plug the y-coordinate in for y, what you end up getting is that the derivative here is about 0.38832. So it's not steep, but it's positive, and we can see in that blue line, yeah, it has a positive slope. It's a small positive slope. Great. I'm going to do this other point, the green one. So if we take the derivative and we evaluate it at, again, x is 1/4, but y is negative 0.271457, what we end up getting is that the derivative is about negative 1.46564. So it's a negative number, and it's steeper. It's still not super steep. And that's what we see in this green line here. We see that we have a larger negative slope. So again, the point is, when we have a curve like this that is the set of solutions of an equation, we can take our y variable and treat it as if it was a function of x, and we can compute dy dx using the chain rule. And now what we get from that will give us the slope of the tangent line if there is a tangent line, and also if we plug in both an x and a y coordinate.